In this question, we're shown this molecule D-glucose, and we're told that when subjected to these reaction conditions, which are known as the Wohl degradation, it converts D-glucose into this molecule over here called D-arabinose. It also tells us that if you take D-mannose, which is a stereoisomer of D-glucose, and subject it to the exact same reaction conditions, it gives you the exact same product. So what does that suggest? The correct answer to that question is B, that glucose and mannose are C2 epimers. Now if you want to know why, I'll go ahead and explain it to you on the board right now. In this question we're shown D-glucose, and we're told that when it's subjected to Wohl degradation conditions, it converts D-glucose into D-arabinose. Now if you don't know what Wohl degradation conditions are, I'll post a link right here to a previous lecture in which I talk about them and actually show you why they work. Essentially what Wohl degradation conditions do. Wohl degradation conditions chew off this part of the molecule and convert this into a double bond. And you can see that's exactly what's happened as we move from the left to the right. When I take D-glucose and subject it to Wohl degradation conditions, it converts D-glucose into D-arabinose, shown there. The question then tells me that when I take D-mannose and subject it to the exact same reaction conditions, that is Wohl degradation conditions, it also yields the same product, D-arabinose. What does that mean that D-mannose looks like? Well, D-mannose must have some kind of aldehyde group up here, and then it's got an OH down there, and I haven't left myself enough room here. As you look at D-arabinose, you'll notice that the three bonds right here have a HO on the left, an O on the right, and an O on the right. Is that politically incorrect? It's got an HO on the left, and then an OH and an OH on the right. So I've got that in my D-mannose. Remember that the Wohl degradation conditions are going to chew off this part of the molecule. Like all sugars, D-mannose must have an OH either on the left or on the right of this bond. Is it going to be on the left or the right? Well, it can't be on the right because glucose has its on the right, and if we had an OH on the right, then this would just be glucose, which means that D-mannose must be the opposite. It must have its OH on the left. Now keep in mind that Wohl degradation conditions just chew off this top group and convert this into a double bond. So if I were to take D-mannose and if it looked like this, and I chewed off this group right here, converted this into a double bond, that would make this carbon atom right here not a stereocenter anymore. That carbon atom would not be a stereocenter anymore because it would only be bonded to three things in a trigonal planar geometry, as is the case right here. See, it's bonded to a hydrogen, it's got an oxygen and a carbon. That's three things, trigonal planar, not tetrahedral, not a stereocenter anymore. So what does that mean D-mannose and D-glucose are relative to each other? Well, every single one of these carbon atoms down the spine of this vertebrae are all stereocenters right here. These are all stereocenters right here. It means that D-mannose must have the exact same stereo configuration at each of these stereocenters as D-glucose, with the exception of the top one. The top one's different for D-mannose than it is for D-glucose. What does that mean? Well, if you've got two molecules where molecule A has a pile of stereocenters, molecule B has a pile of stereocenters, and they look exactly the same at every single stereocenter except one, we have a special word for that. Those two molecules are, of course, diastereomers. That's a generic term, but we have a special word for that type of scenario. One where you've got multiple stereocenters, two molecules, and they're exactly the same except for one stereocenter, and that term is epimers. Hence, the correct answer to this question is that D-glucose and D-mannose are epimers.